An important thing to note when you're dealing with probability activities for students is that not all students have the same background with maybe playing cards or rolling dice, or even in flipping a coin, as surprising as that might be. So you would want to make sure that you clearly set up any type of scenario that you're going to use to teach probability. So the most common one is a coin toss. The reason this is a useful form for probability is because the sample space is pretty small, right? Sample space meaning, remember last time we talked about a sample space is a listing of any possibilities, right? And there's only 2 possibilities with a coin toss, okay? In most state testing, they'll use the term fair coin toss. And that just implicates or implies that each side is equally likely. Kind of like we would assume a coin toss would be, right? Okay. Another really common tool to use for probability is the use of a die, or plural is dice, okay? But in Texas, we don't like to use the term dice, or they don't like to because they say that that's akin to gambling. I think that's a little ridiculous. But they will use terminology like fair 6-sided number cube. To me, that is more confusing than just saying a die or a dice. But nonetheless, that's the terminology that they're likely going to use. Okay, fair meaning that it is just as likely to land on one number as it is the other. So if we wanted to list the sample space for a die, it would be 1, 2, 3, 4, 5, 6. Now I know last time I showed you some non-standard dice, right? But the standard die just has 6 sides. Okay. Another common tool for probability is things like marbles in a bag. I've seen that on standardized testing quite a bit. Okay. But when you want to get a little more fancy or challenging, a lot of times we'll refer to a deck of cards because there's a lot going on in a deck of cards. You know, a coin toss, we only have 2 options. A die roll, we only have 6 options, however many marbles we have in a bag. But a deck of cards, you can really kind of vary your questioning a lot because there are 52 cards. So hopefully this is something that you went and practiced. Okay, I'm not assuming that you have a whole lot of background with cards, but you're going to need to know the basics to be able to do some of the probability assignments that I have. There are 4 what we call suits in a deck of cards. They are the shapes that are on the cards, so hearts, diamonds, clubs, and spades. There are 2 colors, red and black. The hearts and the diamonds are red, and the clubs and spades are black. Okay, there are, I don't really know another way to say this. It's not really 13 numbers because some of them aren't numbers, but there are 13 numbers. It goes ace, 2, 3, 4, all the way up to 10, and then we go jack, queen, king. Okay, it's unimportant whether you're playing a game where ace is higher than king. The point is we're just listing the values out. Okay, so there are 13 options, ace through 10, and then add the jack, queen, king at the end. And then lastly, a lot of times we'll refer to face cards. Face cards are literally cards with a face. So they're just the people, the cards with the people on them. So jacks, queens, and kings. A lot of people think that aces are face cards, but again, face cards are literally cards with faces on them. So, all right, so we're going to look at some basic probability and maybe the probability of multiple events occurring. So this is going to be a little step up from the probability we looked at last time. So remember, the probability is just the chance an event will occur. And if we want the formula for probability, it is the number of desired outcomes on top over the total number of outcomes. So in other words, how many opportunities do we have for what we want to happen to occur, that goes on top, over the total number of options on the bottom. So when we get to probability questions where maybe there's a little bit more at stake or where we're writing a little bit more, you're going to see this notation, this capital P of something. Okay, this is literally read as the probability of event A. So it's just literally a shorthand so that we don't have to write the word probability over and over. So let's take some of our common tools for probability and see if we can find out some simple probabilities, and then we'll get kind of more challenging as this lecture goes on. So in a single coin toss, find the probability of heads. So we have two total options, right? We can land on heads or tails. Okay, the probability of heads, our desired outcome, there's only one of those, right? And make sure that you also can change this to a fraction and or, to a decimal and or a percentage if I ask. Okay, so you change, remember, a fraction to a decimal by dividing, and then you move the decimal place slash, multiply by 100 to change a decimal to a percentage. So what about another one of our common tools for probability? So in a single roll, find the probability of less than 4. Okay, so first let's talk about how many total numbers we have. Okay, on a normal die we have 6 numbers, right? How many of those numbers are less than 4? 1, 2, and 3, right? So we'll get 3 out of 6. You do need to reduce fractions whenever you get them, especially in probability. So this would be also 1 out of 2 or 0.5 or 50%. Okay, so let's look at an example of a single event marble problem. So in a bag of 10 marbles, 2 are blue and 8 are yellow. And I want you to find the probability of doing one draw. We're going to assume that's the case unless they tell us otherwise, and getting yellow. Okay, so remember, probability is on the bottom, it goes how many options we have, right? We have 10 marbles, and 8 of those are yellow. Okay, we would reduce this to 4/5, but this is 0.8 or 80%. Okay, make sure you're moving the decimal place twice, right? This wouldn't be 8%, this would be 80%. Okay, so let's look at some problems with the deck of cards. The good part about these problems is there's more options for you to ask your students. Okay, there's also, more opportunity for you to kind of make it a little more challenging for them. Okay, but there's also a little bit of opportunity for confusion, so you want to make sure, again, like I said before, that everybody has kind of the same background with cards, or at least that you let them play with cards and kind of get caught up if they haven't had a whole lot of experience. So I want to talk about 2 different ways we could talk about some of these card examples. Okay, we could look at how many cards there are in a deck, and if we do that, there are 4 kings out of 52 cards. So that's a perfectly acceptable way to think about this fraction. Okay, or we also could think of it in another way. Okay, we could think of it that there are 13 options, and we just want to talk about one of those options. But notice if we were to reduce 4 out of 52, we would get 1 out of 13. Okay, so if you change this to a decimal and then to a percentage, it's 7.69%. Notice I used the squiggly equals because we're just doing approximate. All right, so let's look at the probability of the card being red. So again, if we look at the fact that there are 52 cards in a deck, 26 of those are red. Okay, so that's one way to look at it. Or we could look at it a little more simply for this problem. We could talk about that there are 2 colors and there's one option that fits our requirement, which is the fact that it's red. Okay, but either case, again, notice that 26 out of 52 just reduces to 1/2. Okay, so this would just be 50%. Notice I used the straight up equal sign because I'm not rounding this time. All right, so what about the probability of the card being a heart? So we can talk about the whole deck. There are 52 cards, right? A fourth of them are each suit, right? So there would be 13 hearts. But notice we also could have talked about the fact that there are 4 suits, right? Hearts, diamonds, clubs, spades, and one option that fits our requirement, which is hearts. Notice I also used the term a quarter when I talked about how many of the cards were, of the 52 were hearts, right? So I kind of already knew it was 1/4 even with the way I was saying that. This works out to be 25%. And then last but not least, and we'll move on to something a little different, okay? What about the probability of a face card? So there are 52 cards, okay? The face cards are the jacks, the queens, and the kings, and there are 4 each of those. So 3 different types of cards, 4 each. There would be 12 total face cards. Okay, so you could start off with this fraction and reduce it, or again, you could remember that, hey, there's only 13 options, and 3 of those options are face cards. So I'm going to kind of squeeze this in here. Okay, so if you divide that out and multiply by 100, this is about 23.08%. On the homework, on the test, just make sure that you pay attention to what form I asked the answer to be in. I think on the homework I asked for a reduced fraction, a decimal, and a percentage, just to kind of get you practice in all 3 forms. Okay. All right, but what about when we want to talk about more than one event occurring together? So we have a couple of terms before we can really kind of move on with this. Terms that you need to know if you're going to structure probability questions, because sometimes probability questions can be a lot more challenging than we really intend them to be. So you need to be aware of events that are independent of each other. Okay, independent events are 2 or more events in which the outcome of one does not affect the outcome of the other. And the reason we need to know whether or not things are dependent or not is so that we can properly find out the probability of a second event if a first one has already occurred. Okay, so the best kind of real life example I can think of this is that people often mistake this when they're having children. So you ever known a family that has like maybe a bunch of boys or a bunch of girls? So I knew a family that had 4 girls. They really, really, really wanted a boy. Okay, so their logic was, we've had 4 girls, so the 5th one is bound to be a boy. Okay, the problem with their logic, although they really, really wanted that boy, is that each time you have a child, what's the chances that that particular child is going to be a boy or a girl? The probability, if you have a child anytime, the probability of it being a boy is simply 1 out of 2. Okay? So in other words, the X and Y chromosomes don't care on the 5th child what the previous 4 children were, right? It is what it is, right? Whatever the genetics say the baby will be, it'll be. Okay? So the reason we need to know this is because if we know that the events are independent of each other, then if we want the probability of A and B occurring, okay, by the way, just to make sure we know this, what this is saying that both A and B occur. So as long as you know that they are separate from each other, or you've taken into account any changes you need to make for the second one, if any, then you can just multiply the probabilities. Okay, so the probability of A and B both happening is just the probability of A times the probability of B. Okay, so this is one formula I'm going to want you to know. The second formula I'm going to want you to know and understand is the probability of A or B. Okay, now that's saying something totally different. This means either one or both. So this is much less restrictive. In the first example, probability of A and B, I'm wanting both events to happen. But in this scenario, I don't care which one happens. They can both happen, okay? Or one or the other can happen. Doesn't really matter. And so the formula for those dual probabilities is you add the probabilities, okay? But you also have to subtract off the probability that they both could have occurred at the same time. Notice how this one says either one or both, okay? So this little subtraction, this little adjustment is to avoid the same items being counted twice. So we'll look at some examples of that as the lecture goes on. Okay, so you have to be really careful when you do probability questions, but also when you create them for your students that you are clear in what you say. Okay, and that you read what the problem's asking for. If you're writing the problem, that you write specifically what you want to ask. Okay. All right. So what if I asked you for the following? What's the probability that the first child in a family is a boy? Okay, we're going to do these two together. And then what's the probability that a second child is a boy? Okay, so the probability that the first child is a boy is 1 out of 2. Okay, so the probability of the second child being a boy, if you're thinking to yourself, well, it depends on what the first child was, then you have the wrong train of thought, right? Because it actually doesn't matter what the first child was, right? The probability that the second child is a boy is also 1 out of 2. Okay, so note the reason we come up with the same probability is because these events are independent from each other. We already talked about this. The existence of a boy or girl in the first child, makes no difference on the boy or girl being present in the second child. All right, so let's talk about this. What's the probability then that the first and the second child are boys? Now notice, I'm asking for 2 events to occur, right? I'm asking for the probability, and notice I even underlined the word and. I want the probability that the first one's a boy, and also, in addition to that, the second one's a boy, okay? So one way to do that would be to use our formula, okay? When we're doing and, as long as we're sure they're independent, and they are, we can just multiply the probabilities. So 1/2 times 1/2 is just 1/4, okay? Notice if I asked you for percentages, you would change these to percentages, but for now we're just going to deal with them in fraction form. But we also could have come to this answer if we wanted to by listing the sample space. Remember, sample space is just where we list all the options, right? So if this family has 2 kids, they only have limited options, right? They could have a girl followed by a girl. They could have a girl followed by a boy followed by a girl, or 2 boys. Okay. Notice if I asked you by looking at the sample space how many of these options were that we got 2 boys, right? It would be 1 out of the list of 4. Okay, right? So we'd get 1/4 no matter what. So sometimes a listing can help if you're struggling and if you can't figure out what you should be doing. So what's the probability that the first and the second, and let's add a third kid, the third children are boys? Okay, so again, we can talk about this directly since it's an and problem. Each of the individual probabilities are independent, right? So we can just multiply them. Okay, so if you multiply 1/2 times itself 3 times, you get 1/8. Okay, so this is the answer, but let's say that we wanted to maybe look at it another way. Notice the sample space is going to be a little longer for this one, right? Because we have more decisions to make, right? We have more events that need to occur. So what are the possibilities for the genders of their kid, right? Girls, they could all be girls. The first two could be girls. The second one could be a boy, right? We could have girl, boy, girl. We could have girl, boy, boy. Okay, and by the way, these are in really no particular order other than the fact that I tried to stick with that the oldest was a girl for the first four. Okay, so notice that exhausts all those possibilities, right? Now the oldest could be a boy, or it could be boy, boy, girl. It could be boy, girl, boy. And then lastly, it could be boy, girl, girl. Okay, notice there's no other options, right? And we have 1, 2, 3, 4, 5, 6, 7, 8 options, okay? And how many of these list of 8 were they all boys, right? Only 1, okay? So 1 out of 8. So I'm going to show you kind of a strategy that will help you with, you can see that the sample space with 3 events is already getting kind of large, right? And we only have 2 options for each of the individual opportunities. Okay, so what's the probability of no boys if there are 3 kids? So we can look back at our sample space. So sometimes you just need to kind of reframe the question, okay? Figure out what it is asking for, okay? So if there are no boys, what does that mean? That means they are all girls. Okay, and the probability that they are all girls, notice that is also 1 out of 8. If you look at our sample space, there's 8 choices, only 1 of which has them all being girls. So let's kind of use that thinking. Okay, what if I asked you for the probability of 3 kids with at least 1 boy? Okay, let's talk about why that's a little more challenging. I'm going to underline the significant part of that problem. Okay, at least 1 boy could mean 1 boy, could mean 2 boys, could be all 3 are boys, right? In fact, the only thing that it really doesn't cover is the probability that we have no boys at all, right? But let's put that on hold for a minute. If we look at our list, right, is there any boys here? Okay, no, right? So that's the only one that doesn't qualify, right? There's at least a boy here, 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 all the way through. So in 7 out of the 8 possibilities, there is at least 1 boy, right? So we have an 87.5% chance of having at least 1 boy if we have 3 kids. But let's talk about another way we could think of that. Okay, so I'm going to put a star by this. This works for at least type problems when you're being asked for at least. So the probability of at least 1 boy, so we're just looking at the same problem again. We also could have thought about it as the total probability is 1, because 1 stands for 100% if we move the decimal place twice. So if we find 1 minus the probability of the opposite event happening, and what's the opposite of at least 1 boy? The opposite of that would be no boys, right? Okay. So in other words, it would be 1 minus the probability of all girls. That's really what it's saying, right? And notice that if we did that, it would be 1 minus a half times a half times a half, okay? And notice that would give us 1 minus 1/8 or 7/8. Okay, so notice we get the same answer. So I'm just going to say same as above. But notice that might be easier if we were trying to do a problem where we didn't want to list the sample space. Like, notice even with 3 kids, the sample space got quite large, right? So I want us to use that 1 minus strategy to find this, okay? The probability of 6 kids with at least 1 boy. Now, I don't know about you, but I don't want to list the orders out for 6 kids. 3 was already a little tedious, to be honest, okay? But when you see at least 1, it's easiest if you actually transfer this into 1 minus the probability of the opposite. So let's think about what the opposite means, okay? At least 1 boy could mean 1 boy, 2 boys, 3 boys, 4, 5, or 6 boys, right? The only thing it doesn't cover is no boys at all. So we're going to do 1 minus the opposite, Okay, 1 meaning 100%, by the way. So essentially, we're really just doing 1 minus the probability of all girls. So it's going to be 1 minus, now what would be the probability that they were all girls? Well, there are 6 events, and each event has the probability of 1 out of 2 because they're independent from each other, right? So we need 6 1/2s being multiplied by each other. So essentially, we're going to get 1 minus 1 over 64. Think of that like 64 minus, or 64 over 64 minus 1 over 64. So that's 63 out of 64. Okay, so if you had 6 kids, the probability that you would have at least 1 boy would be pretty high, right? It'd be 98.44%. Okay. Notice that's a different question, though, than it would be if I said, if they already had 5 boys, what's the probability that the 6th one is a boy? That would still be 1 out of 2. Okay, so we're just talking about from the get-go, what's the probability that you have 6 kids and all of them are boys? Or sorry, at least 1 is a boy. The probability would be 98.44%. Okay, so let's look at some other kind of dual probabilities, meaning where we want more than one event to happen. So I want you to find the probabilities if you have a bag of marbles with 4 green, 6 orange, and 8 blue. So I want us to find the probability of the following, and they are different, so you need to look at kind of the nuances in what I'm asking. I want the probability of 2 orange in a row if you put the first marble back before you draw the second. And then I also want to talk about what the probability will be if we don't do that. In other words, if we pick a marble and we don't put it back before we draw the second. So I'm going to skip a little space. So 2 orange in a row if you don't put the first back before drawing the second. Okay, definitely different questions. All right, so the probability, let's look at the first one. Okay, the probability of 2 orange. So notice we want 2 events to happen. We want the first one to be orange and we want the second one to be orange. Okay, so even though I didn't write the word and, these are and problems. Okay, which means we need to, as long as we're sure they're independent of each other, we need to multiply those probabilities. Okay, so let's talk about the probability of the first one being orange. We have 6 orange. Okay, if you tally up all the marbles you have 18. Okay, so notice this is the probability of my first draw, right? Okay, so now I need to figure out the probability of my second draw, but notice that the point here is that we put the first marble back, okay, before drawing. Okay, so that means the probability of drawing the orange again, since we haven't changed the marbles at all, is still 6 out of 18. Okay, this represents the second draw. And notice I'm multiplying them as opposed to adding them because this is an and problem. It didn't say the probability of one being orange or the other. Okay, it said the probability of them both being orange. So you can simplify these, and I would really suggest that you do. In other words, if you can simplify the fractions before multiplying, then let's do it. So notice 6 goes into both of those things, right? So we have 1/3 times 1/3. You can always simplify it at the end, but it's just easier to do it as you go. So you end up getting 11.11%. Okay. Notice in all of these, if I don't tell you otherwise, let's just do 2 decimal places for the percentage. Okay, but notice what's changing in the second problem. And notice what's not changing. Okay, notice the first draw is unaffected. We still have 6 out of 18. But the point about the second draw is the change that we made here is we don't put the marble back. Okay? In other words, we have changed the quantity of marbles that is present in the bag. Okay? So how many marbles are now able for us to be drawn since we took one of them out? Only 17. And then we have to think about that. How many oranges are left? We had 6, right? But if we already drew one of them, then that marble's gone, right? So we only have 5. So when you go to reduce this, notice I can't reduce both of them, only the first one. So you'll end up getting 5 out of 51. And if you work that out, you get about 9.8. Let's see what the second decimal place is. 9.80%. Okay, so notice it did change the probabilities, right? It was the same kind of question, but because we didn't put the marble back, then we changed the probability for us getting 2 oranges. So you're going to see some terminology in problems like this and maybe problems with cards. You might see the terminology with replacement versus without replacement. That's just referring to the first item being put back or not, okay, and it does change the probabilities, okay. So with replacement, it's just like what it sounds like. You put the first item back before drawing the second. And of course, without replacement means you don't put it back. Okay, so these dual probability questions, just so you know, are more like middle school problems. Okay, 8th grade is kind of a year where you learn a lot of different processes. Okay, 8th grade math is one of those pivotal years where they just teach them a lot of different stuff. They teach them a little bit of geometry. They teach them a lot of pre-algebra. They teach them statistics. They teach them probability. Okay, so I consider 8th grade to be kind of a hodgepodge year. Okay, so this is kind of probably the grade level that I'm discussing when we talk about more than one event happening. Okay, for elementary school, we tend to stick to one event. We don't worry about, adding in a second event. Okay, but this class is to prepare elementary teachers and middle school teachers, so that's why we're looking at it in a basic way and getting a little more challenging. Even if you intend to teach elementary school, you need to know where they're going to go with this. All right, so let's say I told you to find the probabilities using a regular deck of cards. So if you were going to do a problem like this with your students, you would need to make sure, do my students have the basics of a deck of cards before I, incorporate this in my lesson? All right, so I want to look at a couple of different problems. So drawing a 2 first, and then a 3, and let's say we have with replacement. In other words, we're going to put the 2 back before we try to draw the 3, okay, or put the card back before we try to draw the 3. All right, so we have a couple of choices, okay? We talked about this before. We can either talk about how many cards we have, or we can talk about how many options we have, okay, and it's really kind of up to you. But if I want to draw a 2, that is 1 out of 13 choices, okay. Remember, you also could have said 4 out of 52, but think about that. 4 out of 52 reduces to 1 out of 13, okay. So the first draw, we have a 1 out of 13 chance or a 4 out of 52 chance of getting a 2, okay. Notice the word and. Sometimes it'll show up, sometimes it doesn't. Okay, so in other words, we want to multiply these probabilities. If we put the first card back, notice we're to a full deck again, right? So the chances that we get a 3 is also 1 out of 13, okay, or 4 out of 52. It's just by doing it this way, we eliminate the need to have to reduce at the end, okay? But if you did 4 out of 52 times 4 out of 52, it would still reduce to 1 out of 169, right? 1 times 1 is 1, 13 times 13 is 169. And so if you notice, 1 out of 169 is not really that likely, right? So 0.59% would be the percentage, okay? In other words, less than 1%, it's not very likely. All right, so let's talk about how it changes it up if we don't have replacement. So let's go drawing a 2 first. And then a 3 without replacement. Notice what is not affected, and that's the first draw. Okay, the first draw is still 1 out of 32, or if you don't like that, you can replace that with 4 out of 52. But notice when we get to the second one, we do need to make a change, right? We can't say out of 52, so we can no longer do this 13 thing, okay? We're going to have to talk about how many cards there are in the deck, because now there's an unusual number in the deck, right? There's only 51 cards left for me to choose from, because one of the cards is gone. But then think about that. We want a 3, right? So here's that word and again. That's why I'm multiplying them, okay? How many 3s are left? So this is different from the marble question. Notice I took a 2 out, so there's still the full quantity of 3s, right? There's still 4. So if you work this out, this is my second draw, right? So notice when we have without replacement, we don't have a choice to stick with this over 13 notation. We have to put it over 51. So you get 4 out of 663. That's as reduced as that one gets. But when you change it to a percentage, you get something just a little bit different, okay, than you got in part A, right? But it is different, okay? 0.60 is a little different than 0.459. Okay, so let's see if we can do maybe an OR problem. We haven't had too many ORs. So what's the probability of 2 or 3 in a single draw? Okay, so we can talk about this in 2 different ways, and I'm going to list kind of both of them. We can talk about, we have a single draw, right? So there's 52 choices. So there are 4 2s and there are 4 3s, right? So there are a total of 8 that are the number we're wanting, right? Okay, and this reduces to 2 out of 13, or about 15.38%. Notice if we would have wanted to, though, because it was OR, we could have said that's the same as 4 out of 52 plus 4 out of 52. Okay, notice if we add those up, we get 8 out of 52. Okay, we didn't have to worry about subtracting off the chance that the single card was both a 2 or a 3. Remember the formula for OR was the probability of one plus the other minus the probability that it's both. Well, in a single draw, right, we can't have them be both a 2 or a 3, so we didn't have to worry about that. But you do need to worry about that with most OR problems. So let's look at this one. So we have the probability of a 2 or a heart. Okay, so remember, OR probabilities is the probability of the first plus the probability of the second minus the probability of both. Okay, so I'm going to write this out. We need the probability of 2 plus the probability of heart, right, minus the probability of both. In other words, don't we have a card that is the 2 of hearts? So we'll talk about that in just a bit. So the probability of a 2 is 4 out of 52, right? There are 4 2s in a deck of 52. Okay. The probability of hearts is there are 13 of them. And the problem is if we don't do this, we're counting one of the cards twice. So the probability that it is both, think about what that means. Okay, this means the probability of the 2 of hearts, that specific card, right? That's what it means to be both a 2 and a heart. It would be literally the 2 of hearts. Okay, so in the end we get 17 minus 1, or 16 out of 52, which reduces to 4 out of 13. And 4 out of 13 is about 30.77%. Okay, so notice, if you literally got out the deck of cards and you were trying to find out the probability that it would be a 2 or a heart, the problem is if you don't do this right here, if you don't subtract off, then you're counting that one single card of the 2 of hearts. You're counting it in both the 2 category and also the heart category, okay, when actually it's a single card, right? We don't want to double count it. All right, and the last thing that we're going to cover with probability, it's kind of an option, but one other way to kind of organize your data or your sample space is with a tree diagram. So some people like this, some people don't, okay? Some people that are more visual learners like this, but let's say that I had a coin toss and I rolled a die and I wanted to know how many options there were. And then maybe after we draw the tree diagram, I'll ask a couple questions. So in other words, we have 2 events. We're going to roll a die and we're going to toss a coin, and we're going to see what possibilities we have. So a tree diagram looks kind of like a tree with branches. So the first event is that I could either toss a head or a tails in my coin, right? But then I have this second event going on as well after, or maybe simultaneous, it really doesn't matter. And notice after I flip heads or tails, right, I have an option of 6 numbers. Okay, and the same thing here, right? Kind of put them close together so you can fit them all. So I could have a heads followed by a 1, 2, 3, 4, 5, or 6 in my die, right? And I could have a tails followed by the same numbers. Okay, so if I wanted to know how many options there are, I can just count the branches at the end. There are 12 options, right? If you wanted to list the sample space like we did for the gender of the children, right, you could say H1, H2, H3 all the way to H6, but then you could also have T1 all the way to T6. So let's see if we can read this tree diagram and see if it'll help us figure out some probabilities. The probability of heads, and we roll a 2. Okay, so the and is significant. So rather than do our formula, let's just look up at our list, right? We want both things to happen. So that means we want to end up specifically here, right? So out of 12 choices, we only have one option that satisfies that we got heads, sorry about that, and a 2. Okay, so we get 1 out of 12, which is right about 8.33%. Okay. By the way, this is the same thing we would have gotten if we would have done the old way, right, which is the probability of heads is 1 out of 2. The probability that I roll a 2 is 1 out of 6. Notice that equals 1 out of 12 also. Okay, so let's look at the probability of heads or roll a 2. Okay, and this will be the last one we do today. All right, so on the one hand, let's look at it some different ways. We have 12 choices, right? Now notice, this time we want heads or we roll a 2. So let's circle the ones that would qualify, right? Any of these qualify, notice, because we have heads, right? But also that qualifies. So notice if we were to add them, we would get 7 out of 12. Okay, and that works out to be 58.33%. So with a tree diagram, you can sometimes come to your answers without having to have a whole lot of formulas. Okay, but let's talk about how we would get the same formula if we did it this way or the other way. So remember, or means the probability of the first, right? Well, the probability of the first is 1 out of 2. That's the probability of heads. And then we're going to add that to the probability of rolling a 6, right? So this is the probability of, sorry, rolling a 2, not a 6, but it's 1 out of 6. But then notice we're counting the probability of that happening together, right? We're counting this particular instance twice, okay? So that's the problem. We don't want to count that twice, right? So we have to take off the probability that it is both. And notice in the end, a little more challenging though, we end up getting 7/12 again, right? Okay, I actually think in this way the tree diagram is a little easier to just go up and count our desired outcomes, right? All right, so just remember, we need to understand things like probability more so than even the level that we could possibly plan to teach. Okay, so even if you're at the elementary level, you need to know what the eighth graders are going to be teaching. Okay, if you're teaching middle school, then you certainly need to know that middle school level probability.